Pascal's Triangle. So a long time ago, back in the 17th century, in 1600s, we have someone named Pascal, Blaise Pascal. He came up with this special triangle at a very young age. And I wanted to show you this triangle. It has many, many different special properties. And you may have seen this triangle back in grade 11, some depending on which math course you took, or even before that. But it's a very nice triangle, and you'll see why. Okay, so here is what Pascal's triangle looks like, and you'll notice that there are a series of numbers of ones. Let me just highlight this here. So the triangle is constructed starting from what we call row 0. Okay, so the very first row it's labeled row 0. You have to start from 0, and it's just the number 1. Okay, and you go down the triangle diagonally to the left. You'll notice a series of ones, and then diagonally on the right, we also have 1, 1, 1, 1, 1, 1. So a triangle has to start off with this 1 on row 0 and the 2 ones here on row 1. But everything else in the triangle can be constructed, or all the other numbers can be come up with based on just having these ones. Okay, knowing that the every row in the triangle starts off with 1, and every row in the triangle ends with a 1. Now, every number on the inside, so looking at this number 2 is formed by adding the 2 numbers directly above to the left and to the right. And I just didn't set my markers correctly here, so let's set that back to red. That. Yeah, okay. And what is this? Okay, so let's just fix that, delete that. Okay, so the number 2 can be found by just adding the 2 numbers directly from the left and to the right. So this 1 plus the 1 there gives me that 2. Okay. Same idea when I go down to the number 3. I can get the number 3 by adding the 1 from the up to the left and the 2 from the diagonally to the right. So 1 plus 2 gives me 3. Same thing over here. The 2 plus the 1 over here gives me that 3. And then the 4 can be obtained by adding the 1 diagonally from the left and the 3 diagonally above from the right. So again, 6, same thing. 6 is 3 plus 3. 4 is 3 plus 1. And so on and so on. You can come up with the rest of the triangle in this fashion. So if I look at the row number 5, so you start off with your row, has to start off with number 1. But every other number can be the addition of the 2 diagonal numbers from the left and from the right. So 1 plus 4 gives me 5. 4 plus 6 gives me 10. 6 plus 4 gives me 10. 4 plus 1 gives me 5. And there is row 5. And if I go down to row 6, again, you must start off with the row with number 1, and you must end the row with a number 1. But everything else in between comes from the addition of the 2 numbers above it. So 1 plus 5 gives me 6. 5 plus 10 gives me 15. 10 plus 10 gives me 20. 10 plus 5 is 15, and 5 plus 1 is 6. Okay, so how does this triangle work again? I'm going to write down exactly how it is in your notes. So each term is equal to the sum of the 2 terms immediately above it. The first and last terms in each row are 1, since the only term immediately above them is 1. Okay. Now, you can imagine this triangle can go on forever. You can go row 7, row 8, row 9, row 10, row 100, row 200, row 1000, row 10,000. It can become really, really big. Okay. Now, I'm not going to ask you to construct the Pascal's triangle of 1,000 rows, but there is a way to find any term in Pascal's triangle using a formula. So what kind of formula would that look like? So let's start off with what I have here. So if this term here, it's called T with the subscripts N and R, represents the term in row N and position R, then for any term T and R, we can express that as t of n minus 1 comma r minus 1 plus the term that is t of n minus 1 comma r. So let me explain this formula just a little bit here. So look at the Pascal's triangle now written as term numbers. So if you're on row 0, then the term up here, you know it's a 1, but it's just labeled t of 0, 0. So 0 stands for the row number, 0 stands for the position. So you always have to start your labeling from 0. Looking at this row number 1, so n is the 1, this n is 1, and this n is 1, so these two refers to the row number, and the 0 and the 1 refer to the position, and you're going in order from 0, 1, 2, 3, etc. So again, as you look at the r, so 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4, etc., etc. And then the n values 1 and 1, 2, 2, 2, 3, 3, 3, 3, 4, 4, 4, 4, corresponding to whatever row you're in. So that any term that you obtain, that you want, n of r, so let's say I wanted t of 2, 1, how would I find 2 of 1? Well, I just take whatever the value of n is, which is 2, subtract 1, I get 1. 1 subtract 1 is 0. So I just go above to the left, 1 comma 0. And I add it to the term that is at minus 1, so t of 1 and comma 1. So t of 1 and 1 right here. So I add to that value there just so I can get that. So basically, this is just a general way of expressing how to find the term as the sum of the two terms immediately above it. Okay. Now I can rearrange the formula to solve for those two other terms. So if you're given the term in the bottom, you can rearrange it so you can get something that looks like this. So t of n comma r minus t of n minus 1 comma r, and you can also find the term. This is the how you find the term on the left. If you want to find the term on the upper right, you can just say t of n comma r minus t of n minus 1 comma r minus 1. So these are just the ways to find the terms on the above left and the above right. So I'm going to write that here, left and right. Okay. So investigating the row sums in Pascal's triangle. So find the sum of the numbers in each of the first 6 rows of Pascal's triangle. So the sum of numbers in row 0. Well, all you have is a number 1 in row 0. So the sum is just 1. What about in row 1? Well, you have 2 numbers. So the 2 numbers in row 1. So I have here the 1 and 1. And I add them together, I get 2. What about row 2? If I look at the number in row 2 here, I have 1 plus 2 plus 1, which make 4. Row 3, I get 1 plus 3 plus 3 plus 1, which make 8. And if you do row 4, you get 16. And if you do row 5, you get 32. And you do row 6, you can add them up and you'll see you get 64. So how can I predict the sum of the entries in rows 7, 8, and 9? Well, if you look, there's a little pattern going on in Pascal's triangle. It's doubling. From 1 it goes to 2, it doubles again to 4, it doubles again to 8, and doubles again to 16. So at row 6, I'm at 64. If I want to get row 7, I can just, using the pattern, I can predict that I can double with 64, and I'll get with the number in the sum of the row number 7. So that sum is going to be 64 plus 64, which is 128. Likewise, row 8 will be 128 plus 128, which is 256. And row 9 will be 256 plus 256, which should really be 512. So is there a formula to express this doubling effect? And in fact, there is. So if you want, it's an exponential function. So we can say that the sum of each row is equal to, if it's a doubling effect, you're going to need to use the base of 2, and my exponent will just be the row number. So if it's row 0, then 2 to the power of 0 is 1. If it's row 1, 2 to the power of 1 is 2. Row 2, 2 to the power of 2 is 4. Row 3, 2 to the power of 3 is 8, and so on and so on. So this is the formula that we can use to express the sum of entries in any row of Pascal's triangle. Let's go down to example 1. The first 4 terms in row 25. This is now row 25. I'm not going to ask you to make a triangle all the way to row 25, but you can now use some of these formulas to help us solve some problems. So we're told the first 4 terms are 1, 25, 300, and 3200. So determine the first 4 terms in row 26. In row 26. So keep in mind that if this is row 25, then row 26 will look something like this. Once you're going to start off with the number 1 here. You're going to add up those 2 numbers to get this. Add up these 2 numbers to get this number. And add up these 2 numbers to get this number. Okay, so I can get the first 4 terms. So they would be 1, 1 plus 25, which would be 26. The next term would be 25 plus 300, which would be 325. And the fourth term would be 300 plus 2,300, which should be 2,600. Okay, part B. Determine the first 4 terms in row 24. So now we're not going to go further ahead. We're going to go 1 row backwards. So it turns out if these 2 numbers, there will be a number up here, there will be a number up here, there will be a number up here, and there will be a number up here if I'm trying to kind of reconstruct what that triangle looks like. Now we already know the first row of every row in Pascal's triangle. That's going to be a 1. So I already know the first one is going to be a 1. Well, what about the next one? Well, if I already know that this number plus this number gives me 25, then by induction, I can say this is going to be 24, or I can say this is 25 minus 1, which is 24. So you can just either deduce it from just looking at the pattern, or you can use the formula that I gave you up here. If you want to find the term on the upper right, just use this formula. Okay. So I'm going to write here 24, and then to get the 300, well, I can just say 300 minus 24 gives me that third term on row 24, which is 276. And the fourth term is going to be 2,300 minus 276, which is 2,024. Okay. So it's a little bit of an iterative process because you couldn't find these later ones unless you knew the ones that came before it. Part C, use Pascal's method to write a formula for each of the following terms. So if I wanted to find T of row 12 in position 5, well, I can go back to the previous row. So T of row 11 in position 4, which is the upper left, plus the term in the upper right, which is T of row 11, position 5. Similarly, for row 40 and position 32, well, I can take the terms in row 39 and on the upper left, which would be position 31, and add it to the term on row 39 on the upper right, which would be position 32. And last term, in more general terms, if you have T of n plus 1 and r plus 1, then the term on the upper right would just be the row before, T of n, comma, r, that would be in the upper left, plus the term on the upper right, T of n, comma, r plus 1. Example 2, which row in Pascal's triangle has the sum of its terms equal to 32,768? So this is a little bit more of an algebraic problem. So how do we know what row that number would that be in? I mean, like, are you going to reconstruct this triangle? Well, no, you're not, because you already know the formula for the sum of the rows. So I'm going to write here the sum of the terms in a Pascal triangle row is given by 2 to the exponent n. So we know the sum is going to be 2 to the exponent n equal to 32,768. Now all you have to do is solve for n. Now you have to go back to just your grade 11 course. So if you took grade 11U, you may have been taught how to solve for n using logarithms. If you took the grade 11 mixed course, you may not have, but a logarithm is just an operation that you can use to solve for unknown value and unknown variable if the variable is an exponent. Okay, and so I'm just going to show you here. If you took the log of both sides, so let's just transform this equation. Say the log of both sides. Think of it as if, or maybe I'm dividing both sides by something, or I'm multiplying both sides of the equation by something. Same thing. You take the log of both sides, and so that you get something that looks like this. And there's a rule in logarithms, if you may recall, that if you have a log of some argument here, and that argument has an exponent, you can move the exponent to the front. So I can move this exponent n to the front and write it as n log 2, n times log of 2, which is equal to log of 32,768, which would allow me to rearrange this for n by dividing both sides. So n equals the log of 32,768 divided by the log of 2. And that's going to equal 15. And so that says row 15 is the one that in Pascal's triangle that will have a sum of 32,768. Okay, example 3. Coins can be arranged in the shape of an equilateral triangle as shown. So I have these coins rearranged as an equilateral triangle. Continue the pattern to determine the number of coins in triangles with 4, 5, and 6 rows. So here I have one row, and I just have one coin. Here I have 2 rows, I have 3 coins. And here I have 3 rows, and I have 6 coins. And what would 4 rows look like? So I'm going to just say 4 rows, and I'm going to draw some coins. So here I have 1, continue the pattern, and I should have something that looks like this, right? Just add another row. Okay, and it turns out if you notice the pattern, if you have one row, you have one coin at the bottom row. If you have 2 rows, and your bottom row has 2 coins. If you have 3 rows, your bottom row has 3 coins. If you have 4 rows, the bottom row better have 4 coins. Okay, then I add them all up, I have 10 here. If the triangle has 5 rows, it's going to look something like this. So you just draw the one that you had for 4 rows. Then you add your 5th row. 1, 2, 3, 4, 5. So now I have 15 coins in here. And then I have 6 rows. Same idea. Draw the one that you had for 5, and then add one more row. So here's the one I had for 5, and if I add one more row, 1, 2, 3, 4, 5, 6, and this one is 21 coins. So now if I continue the pattern, what's happening? Every time I increase by the number of rows, I'm just adding that row number. So if I go to row 7, just add 7 more. So 21 plus 7 is 28. If I go to row 8, you add 8 more. 28 plus 8 is 36, and so on. Okay. So let's fill in my table here. So I have 1, 3, 6, 10, 15, and 21. And I'm going to move on before I fill in that last row here. Well, I mean, it turns out that if we have, depending on the number of coins, which is n, then you could say the number of coins that you have in total will be the sum starting from row 1 all the way to row n of the number of coins in each row. And that's how I can express that mathematically. Okay, part B, locate these terms in Pascal's triangle. Locate these numbers in Pascal's triangle. So where can I find 1, 3, 6, 10, 15, and 21? I can find that If I highlight, I can find that here: 1, 3, 6, 10, 15, and 21. And I can also find it here: 1, 3, 6, 10, 15, and 21. Now, I'm gonna need to use this particular these numbers in this particular location. But which one I'm going to use is not going to be this one. I'm going to use this one here. And the reason why is because this diagonal of numbers has a constant row number. R is constant. So I'm going to say here, use this one since the position number R stays constant. R equals, what is R? So if you look at carefully, it's a 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2. R is going to be 2, 2 down this diagonal. So R equals 2. Okay, so let's relate Pascal's triangle to number of coins in a triangle with n rows. So here I'm going to say the number of rows of Pascal's term is one more than the number of rows in the triangle shown. The position number is always 2. So we're talking about here, if the term number is t of n plus 1, and the row number, the row is n plus 1, and the position is 2. Okay, so like if you look at this row right here, this is row number 0, 1, this is row number 2. This is row number 2, but and then R value is 1. But in the example, it's row 1, one row of coins. Okay, so the row number in Pascal's term is 1 more than the number of rows in the triangle that we have up here. Okay? Same idea. So here, row number 3, the position is 3 has 3 coins, but I have 2 rows in my triangle. So always going to be 1 more. T. That's why we have t of n plus 1. The term in Pascal's triangle is n based on the number of rows in the triangle given. If I add 1 more to that, I will get the correct location on Pascal's triangle. So how many coins are in a triangle with 12 rows? Then that means I need to find the value in Pascal's triangle at row 13. So it's t of 12 plus 1, comma, and position is always 2, so I'll leave it as 2. So it's t of 13, comma 2, which is the sum of all the rows from 1 to 12, and that is, think about 1 plus, so if you add 1 plus 2 plus 3 plus dot 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 plus all the way to 12, you will have 78 coins. And I'm just using the formula that I have up here. Okay, so determine Pascal's triangles. How do I express this to determine Pascal's triangle? Well, this is going to be, again, row of coins. If it's 1 row in the triangle, it's going to be row 2 in Pascal's triangle, 2 of 2. Here I have row 3 of 2, 4 of 2, 5 of 2, 6 of 2, 7 of 2, and then n plus 1 of 2. So applying Pascal's method. So I'm going to ask you to do these activities as a class. So you have 1, 2, 3, 4, 5, and 6 activities. We're going to take them up together, but I need you to try them first, and you can work as your usual groups and go through them. So you can pause the video now at this point. Okay, so applying Pascal's method on this first activity. So how many paths will spell November if you start at the top and proceed to the next row by moving diagonally left or right? So hint, trace the path downwards just like in Pascal's triangle. You add the two cells directly above it to get the total number of paths. So go from N to O. There's only, think of like Pascal's triangle, right? There's one way to go down this row. Okay, and on the right and I'm diagonally on the left, right? So, but to go to V, well, I can go N to O to V and then N O to V. So there's two ways to get here. Okay. How do I get to E? Well, I can go N-O-V-E, N-O-V-E, or N-O-V-E. So there's three ways. And if you notice, it just follows the pattern of Pascal's triangle. So I can just write out everything like Pascal's triangle. And this is a way of just being able to tell how many paths are there to get from the very top letter to the very bottom two letters, or two R's at the bottom. And so if I finish this 15, 20, and 15, and in the final row we have 35 and 35. So I'm just adding the two numbers in the left and right above it to get 35. So how many paths are there to get to this R from N to R? I get 35 paths. To get to this R, I have 35 paths. So the total number of paths is equal to 35 plus 35, which is 70. Okay. Now there's a way to do this using permutations or combinations. So another way of looking at it using permutations as well. Okay, what if I go down on a basic path from N to R? So I can go down 1 to the right, 2 to the right, 3 to the right, 4 to the right, 5 down, 6 down, 7 down. So I have 7 letters to hop over to get from N to R. So how many ways to get from N to R? Well, there are 7, because it corresponds to 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6, 7, 7 rows that I have to get through. So there are 7 factorial arrangements here, except, however, if you look at it carefully, if you look at these problems, if you're going either to the right or to the left, well, how many ways are there going to the right? Well, I have 1, 2, 3, 4, and 1, 2, 3. So the one potential arrangement of paths I can take is I go down right, 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 right. So right, 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 right. So 4 times, and then left 1, 2, 3. So left, left, left. I could also go this way. So let's pick a different path. So 1 to the left, 1 down to the right, 1 down to the right, 1 down to the left, 1 down to the right, 1 down to the left, and 1 down to the right. So what's the potential way of doing this now? So I have 1 to the left, 1 to the right, 1 to the right again, that 1 back to the left, to the right, to the left, to the right. Okay, so again, 7 ways, 7 paths, 7 letters I have to go over. How many R's do I have? 1, 2, 3, 4, and then I have same thing. I have 4 up here, 4 here. I have 3 L's here, 3 L's here. Okay, so it's just basically how many ways I can arrange these R's and L's. However, remember, although I'm saying this is a permutation problem, this is a permutation problem with identical elements. Okay, these are non-distinct elements. So if you remember how to do this, you just simply take your 7 factorial and you divide by, well, I have 4 repeated identical R's, so I have to divide by 4 factorial, and I have 3 repeated L's here, so I have to also divide by 3 factorial. And if you carry out that math on your calculator, so 7 factorial, and just quickly doing this on my calculator, You should get the same answer, but I just want to make sure I see for myself here. So here, 35. So that's right. So you get 35 ways to get from this n to this r. And then again, if you add, don't forget the fact that you have to also get, or you could also get to this r. If it's an or problem, you have to add 35 plus 35, and that's where you get the 7. Okay. Another way of looking at this is not through a permutation problem, but rather a combination problem. So if you have to go 7 paths, so 1, 2, 3, 4, 5, 6, 7. So you have 7 paths to go from n to r, and you know that 4 of them have to be r's, going to the right. So I could say this could be going to the right, this could be going to the right, this could be going to the right, and this could be going to the right. So it can become a combination problem where I have 7 paths to choose from, but I had to make 4 of them r's. So if we do 7 choose 4, you also get 35. Now, after you arrange the r's, you know everything else is going to be l's, going to the left. So to get from 1 to r, I have 35, and then to go from the n to r on the other r here, I also have another 35, which will also get you to 7. There's more than one way to solve this problem. Okay, so I'm going to stop the video here, and I'll take up the rest of the activities with you in class.